We're special.
Lumen not school too.
What?
Lumen's not school too.
It is. All right. So logarithmic differentiation. Here's kind of the why this exists. Why this is helpful or useful. Okay, need your attention up here, please. Suppose I asked you to differentiate this function, y equals x to the square root of x. So we have two rules. We have the power rule and we have the rule for exponential functions. Neither of them would work to find the derivative of this function, y. Why could I not use the power rule? The power rule says if you have the derivative of a term in the form x to the n, it's equal to n times x to the n minus 1. Why can't I do that here? Connor?
Because I think wouldn't you have to use chain rule because it's a function inside of a function?
Well, it's a function inside of a function. So yeah, chain rule would probably be the case, but why could I not use a chain rule with the power rule, okay?
For the power rule, n is like an integer, which is a constant, and x is a variable.
Yes, n here is a real number. The square root of x in this case is a variable. So the power rule doesn't work because the exponent of the square root of x is a variable. So it is not a power function. To be a power function, the exponent has to be a real number, not a variable. Why does the rule for exponential functions not work? So that would be if you have the derivative with respect to x of an exponential function of the form a to the x. This is a to the x times natural log of a. But why would that not work? Because there the exponent is a variable. So it would still involve a chain rule. But why does it still not work? Because x is raised to it in an exponential function, the base is supposed to be a constant. Here our base is also a variable. So this doesn't work because the base of x is a variable. Okay, so the two rules we would have that we would kind of be drawn to try in this situation, neither of them would work because of the type of function it is. The base is a variable, so is the exponent. This is where the process of logarithmic differentiation allows you to find the derivative of that function. So this is what, or these are the three main steps. Now within those three steps, there could be multiple other steps, but the three main steps you need to know. The first step, and we actually are going to find the derivative of that function first, is to take natural logarithms or take the natural log of both sides of the equation and then use laws of logs to simplify. And we've already practiced using the laws of logs to simplify just from yesterday, rewriting functions before we actually take the derivatives. So I did include the three laws. When you have the natural log of a product, it's the sum of the two logs. Natural log of a quotient is the difference of the two logs. Natural log of something to a power, you can bring that power down in front. Then, after you take the natural log of each side and simplify using laws of logs, you differentiate implicitly with respect to x. So you take the derivative with respect to x of both sides, and then you solve for dy dx. So it's basically take the natural log of each side, simplify, and then use implicit differentiation to find your derivative. So in example 1, we're going to find the derivative of y equals x to the square root of x. So step 1 is to take the natural log of each side. So natural log of y will equal the natural log of x to the square root of x. And then the left side of your equation is always going to be natural log of y. The right side of your equation you simplify using laws of logs. So I have natural log of y equals, what can I do to simplify this?
Bring it down.
Yeah. So I have square root of x times the natural log of x. Divide by what? You don't want to divide by natural log of x. Nope. Because we don't have a derivative yet. We're trying to take the derivative. So once you have taken the natural log of each side, you have simplified the right side as much as you can. In this case, there was just one thing we needed to do to simplify using laws of logs. Then you differentiate with respect to x. So I'm taking the derivative with respect to x of the natural log of y and the derivative with respect to x of, I'm going to write the square root of x as x to the 1/2 because when I'm taking the derivative, that'll be easier, times natural log of x. So differentiate both sides. On the left side, you are differentiating implicitly because you have the natural log of y. So we know the natural log of y, that derivative from yesterday would be 1 over y, but because it's y, you have to multiply by dy dx, and that eventually is what you're solving for in the end. On the other side, everything is already in terms of x, so you're just taking the derivative using the appropriate rules. What do we need to find the derivative of the right side? Product rule, I heard. So first is x to the 1/2, second is natural log of x. Derivative of x to the 1/2 is 1/2 x to the negative 1/2. Derivative of natural log of x is 1 over x. So then first times second prime is going to be x to the 1/2 over x, or x to the 1/2 times 1 over x, and that I could simplify. And then plus second times first prime, 1/2 x to the negative 1/2 times natural log of x. Okay, now typically what I'll do here is, and this is up to you how far you want to go with simplifying. I will typically simplify the right side if I can. So just rewrite it to make it look a little nicer. So for example, if I have x to the 1/2 over x to the first, this would just be 1 over x to the 1/2, or 1 over the square root of x. That would be the simplified form. Plus, and then this, if I wanted to simplify it so that I don't have a power of 1/2 and I don't have a negative exponent, it would be natural log of x over 2 square root x. So then, and yeah, could you do more to simplify this? Sure. You could get a common denominator. Again, that's up to you how far you want to go with it. It could be up to how they lay out the answers on the multiple choice test to see what you need to match. But from here, we are trying to find the derivative of y, so we want to solve for dy dx, so that you then just multiply both sides by y. So we have dy dx equals, now I don't want y in my answer, so you then also need to go back to the original function and see what y is equal to. Y is your original function, and I'm actually going to write that in front here. So my final derivative is x to the square root of x times 1 over the square root of x plus natural log of x over 2 square root x. Yes, so I'm just writing the y in front, but you do not leave y in your answer. Your derivative should be completely in terms of x because your function to begin with was in terms of x. So these derivatives, honestly, this derivative doesn't look too bad compared to how some of them can look. They can look pretty complicated. Yeah.
How do you change it from with all the 1/2 to the square root, like the 2 square root
Well, this would be x to the 1/2 in the denominator because it's negative, and then if it's to the 1/2, it's the square root. So that's where that came from, and the natural log is multiplied by it, but it would be on top. And you wouldn't have to do this. I'm just showing you how to simplify it if you needed to for a. Yes, you could leave this. Yeah. All right. Let's take a look at example 2. There's more going on in this function. So, what I do want to point out with example 2 is logarithmic differentiation would not have to be used for number 2. You wouldn't have to use it. You could use the quotient rule. Within the quotient rule, you'd have a product rule, you'd have chain rules. You're basically combining almost every rule you have to find that derivative. You wouldn't need logarithmic differentiation, but it makes it a lot simpler for you to find the derivative. So if I want to use logarithmic differentiation, I start out by taking the natural log of each side. It's logarithmic differentiation. But within logarithmic differentiation, you are using implicit differentiation. So take the natural log of both sides, simplify the right side. So right now the left side is still natural log of y. I'm not taking any derivatives yet. So first of all, I see that I have a quotient. So I can rewrite that as the natural log of x to the 3/4 times the square root of x squared plus 1 minus the natural log of 3x plus 2 to the 5th. Okay, I can still simplify. On that first natural log, I have a product that I can split into the sum of two natural logs. So natural log of x to the 3/4 plus, and I'm going to write the square root as that quantity to the 1/2. So natural log of x squared plus 1 to the 1/2 minus natural log of 3x plus 2 to the 5th. And then all of these natural logs are the natural log of something to a power. All of those powers can be brought down in front. So I have 3/4 natural log of x. And now even if you just look at that one term, now that derivative is going to be simple because it's just the derivative of natural log of x. There's not even a chain rule for that one term. And then plus 1/2 natural log of x squared plus 1 minus 5 natural log of 3x plus 2. And that's still equal to natural log of y. So I haven't taken a derivative yet, but now when I do take the derivative of every term, I'm still using some chain rules, but hopefully this looks less complicated than what we started with. So when I take the derivative of everything, so now I'm just going to write taking the derivative with respect to x of everything on both sides. And the left side is always the same thing. The derivative of the natural log of y is 1 over y times dy dx. And then 3/4 times natural log of x, I'll have 3/4 times the derivative of natural log, which is 1 over x, plus 1/2 times this derivative, so chain rule would be 1 over x squared plus 1 times derivative of x squared plus 1 is 2x, minus 5 times the derivative of the last natural log, chain rule, 1 over 3x plus 2 times the derivative of 3x plus 2 is 3. So I'm going to simplify my right side a little bit, clean up those fractions. So the first one, I can write that as 3 over 4x plus, for the second term, the 1/2 and the 2 will cancel out. The 1/2 and then from the 2x. So I would just have x over x squared plus 1. And then minus 15 over 3x plus 2. And then the last thing I need to do is multiply both sides by y and also rewrite y by substituting in the original function. So with logarithmic differentiation, the original function is always included in your answer. And I usually will write that in front. So I have dy dx, the derivative is equal to, I'm going to rewrite y, the original function, x to the 3/4 times the square root of x squared plus 1 over 3x plus 2 to the 5th times this whole thing here. 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And that is your derivative. You don't need to distribute. You could. This is your y. That's your original function. Okay, so example 3 I want you to do. I did the book assignment that I have listed there. I did actually type the problems onto a worksheet. So I will pass that out. So work on example 3. I'll pass out the worksheet for the practice. I included still the problem numbers, so if you wanted to check the odd ones, you could. And then if you have any questions from this example, example 3, anything like that, let me know.
Are we good to go?
If you're still in here,
Get out.
this is the, oh, come on. This is the right answer here. Yep.
Yeah.